Imagine you're standing outside, completely still. Suddenly, the ground beneath you locks completely in place. No deceleration, just an instant, violent halt. Right now, you're on a planetary treadmill. At the equator, Earth rotates roughly 1,000 miles per hour. Because of momentum, when bedrock stops, everything not physically bolted down keeps moving. The atmosphere, oceans, and you instantly launched eastward at supersonic speeds. The immediate threat isn't the planet stopping, it's that you don't stop with it. There is, however, a geographic loophole. If you were standing at the exact north or south pole, you wouldn't even notice the planet had locked up, at least not at first. This comes down to angular momentum. Think of a spinning basketball balanced on your finger. The equator of that ball is moving incredibly fast, but the absolute top and bottom points have an angular velocity of 0. While that 0 momentum buys the poles a brief moment of peace, the supersonic atmosphere from the rest of the planet is already on its way to catch up with them. Even with the ground completely stationary, the atmosphere continues to drag across the surface. This generates a global windstorm blowing near the equator at 1,000 miles per hour. This chart compares atmospheric extremes. It shows the strongest wind gust ever recorded on our planet, just over 250 miles per hour, against the new baseline of 1,000 miles per hour on a stationary Earth. At this velocity, winds obliterate steel-reinforced buildings and peel the top layer of the Earth's crust directly off the bedrock. There is one strange upside. Without the planet's rotation, the Coriolis effect disappears. The Coriolis effect is the force that deflects moving air masses and creates swirling weather patterns, meaning hurricanes can no longer form. But a lack of hurricanes won't save you. If you somehow survived the supersonic air scraping across the continents, you only have a few minutes before the oceans arrive to finish the job. The world's oceans carry the exact same eastward momentum as the air. Water would surge over the coastlines, sending tidal waves hundreds of feet high, sweeping miles inland across every continent. Deep underground, the Earth's tectonic plates also possess massive kinetic energy. When the viscous mantle beneath them suddenly halts, these slabs of rock violently slam into one another. This triggers massive tremors rippling across the globe. Earthquakes scale up to levels never before recorded, fracturing the remaining crust into pieces. Because oceanic plates are denser than continental plates, they are forced underneath them in the collision. This pushes molten lava to the surface, causing massive volcanic eruptions that pump smoke and ash into the sky. In a matter of minutes, a lush blue planet is reduced to a scarred landscape defined by boiling water and liquid rock. This cross-section shows the shape of our current oceans. As the Earth spins, it creates centrifugal force, an outward physical pull that draws ocean water toward the equator, piling it up into a bulge roughly 13 miles higher than sea level at the poles. Without that spin, the centrifugal force vanishes. The sea level at the equator immediately drops by about 5 miles, and all that water rushes away toward the gravitational centers at the north and south poles. This redrawing of the map leaves the Earth with 2 massive polar oceans. In the middle sits a unified, barren supercontinent wrapping entirely around the planet's equatorial region. The only complex life left would be hardy polar animals, like penguins, whose icy habitats have just been completely submerged by the incoming saltwater. The very geography of the planet is inverted. To survive in this new world, life has to adapt to an environment where the rules of day and night no longer apply. Just because the Earth stopped spinning on its axis doesn't mean it stopped orbiting the sun. But without that rotation, one full day of sunlight now takes an entire year, or 8,760 hours, to complete. Whatever side of the planet faces the sun will endure 6 months of continuous, baking light. Temperatures will steadily climb, past 212 degrees Fahrenheit, boiling away any remaining surface water. On the opposite side, it is absolute night for half a year. Temperatures plummet to deep freeze levels, and because the planet is stationary, the constellations in the night sky never move. If humans survived the initial impact, their only option would be to form nomadic tribes. They would have to perpetually migrate around that new supercontinent, staying within the narrow, temperate twilight zone between the boiling day and the freezing night. Biology on Earth evolved over hundreds of millions of years for a 24-hour cycle. With the circadian rhythm completely broken, permanent human settlement becomes physically impossible on this new Earth. The Earth's spin is actually slowing down right now, but at a rate of roughly 1.4 milliseconds every century. This gradual deceleration is caused by tidal friction. As the moon's gravity pulls on our oceans to create the tides, that physical drag acts as a massive celestial brake pad on Earth's momentum. To actually halt the planet instantly, you would need a catastrophic collision with another planetary body in our solar system. Evidence suggests an impact like that is what slowed and reversed the rotation of Venus. Long before tidal friction ever brings our planet to a complete stop, the Earth faces a different expiration date. In about 5 billion years, the sun will burn through its hydrogen, expand into a red giant, and consume the Earth entirely. Until then, the intricate physics keeping our world spinning are incredibly stable. The planetary emergency brake won't be pulled anytime soon. Thanks for watching, and remember to subscribe for more thought experiments.